Linear algebra, lecture 11. I said I would give 2 weeks notice for the midterm. So let's say the midterm exam will be 2 weeks from today, which is Wednesday, October 25th, since today is the 11th, on campus. At 11 o'clock. So it's not an online exam. You have to take it in person, and I'll send out a review sheet, and we'll have a couple of sessions and multiple problem sessions on Zoom where you can ask questions. Okay.
Which room was it in Gillette Hall?
We both can look it up on the website. I don't remember. I think it's 20. I don't want to say, but
oh, it's on the syllabus.
And so we've been talking about matrices, and the last thing we discussed was invertible matrices, the subject of invertible matrices. And so the n by n matrix A is invertible if there is an n by n matrix B such that A times B and B times A are both equal to the identity matrix. I sometimes write just I, or if I want to emphasize, it's an n by n matrix, I sub n. This is the matrix with ones down the main diagonal and zeros everywhere else. So, for example, if the matrix A is 3, 7, 5, 12, I claim that the matrix B, the inverse, is 12 minus 7 minus 5, 3. Is that correct? Let's see. If I take 3, 7, 5, 12 times 12 minus 7 minus 5, 3, I get 36 minus 35 minus 21 plus 21, 60 minus 60 minus 35 plus 36. So if I do my arithmetic, this is the 2 by 2 identity matrix. And if I multiply in the opposite order, matrix multiplication is not commutative in general. So because AB is the identity does not mean that BA is the identity necessarily. Let's see, what do I get? I get 36 minus 35, 84 minus 84, minus 15 plus 15, minus 5 plus 36. Again, that's the 2 by 2 identity. So the inverse of the matrix A is B. By the way, how did I get it so easily? In general, it's a hard calculation to find the inverse, but I showed last week, and not for the first time, that if A is the matrix A, B, C, D, and the determinant of A, which is defined to be AD minus BC, is not 0, then if I take the matrix B, which is, let me call this determinant, just so I don't have to write AD minus BC, I'll call this delta. I write this as D over delta minus B over delta minus C over delta, A over delta, is the inverse. And in the example I just looked at, 3, 7, 5, 12. Then the determinant is 3 times 12 minus 5 times 7. 36 minus 35 is 1. That's my delta. So I'm just dividing by 1, and that made everything easy. Okay. Any questions about this? So you need to be able to just write down a 2 by 2 matrix's inverse if it has one. Okay. And there's a little theorem which says that if A is invertible, then the inverse of A is unique. The matrix has only one inverse, it's unique. So in the proof is as follows. Suppose B is an inverse. AB equals BA is the identity. And C is an inverse. AC equals CA is the identity. So then I can do the following clever calculation. The matrix B is B times the identity, because any matrix times the identity gives you back the same matrix. But I can write the identity as A times C. This is B times AC. Because AC equals the identity. But because matrix multiplication is associative, this is the same as BA times C. And BA is equal to the identity, and the identity times C is C. So B equals C. So if a matrix has an inverse, the matrix is unique, and we write A superscript minus 1 as the inverse of A if it exists. Again, not every matrix has an inverse. A 2 by 2 matrix has an inverse if and only if its determinant is non-zero. We'll see in the next chapter on determinants that we can define the determinant of an n by n matrix, and the same theorem is true. The matrix is invertible if and only if the determinant is 0, but we haven't gotten to that yet. Okay. Another very simple theorem is that if A and B are both invertible n by n matrices, then the product AB is invertible. That's not obvious, but, and the inverse of AB is the product of the inverses of A and B, but in the opposite order, B inverse, A inverse. Right? So A and B are invertible, so their inverses exist, and they're n by n matrices, so I can multiply them. So the assertion is that this matrix is the inverse of AB. And the proof just uses, once again, associativity of matrix multiplication. If I take AB times the matrix B inverse A inverse, that's the same as A times B inverse A inverse by associativity, which is, again is A times, and by associativity in here, B inverse times A inverse. B inverse is the identity. Identity times anything is the anything. So AB times B inverse A inverse is the identity. And in the opposite order, B inverse A inverse times AB is B inverse times A inverse times AB, which is B inverse times A inverse A times B, which is B inverse times the identity times B, which is B inverse times B, which is the identity. So that's the proof. And there's another theorem I'm just going to state at this point, I'll prove later. So that A and B, n by n matrices, if AB is the identity, then BA is the identity. And if BA is the identity, then AB is the identity. So in some sense, if B is a right inverse of A, then B is also a left inverse of A, and conversely. So this actually takes a tiny bit of work and uses some things we haven't proven yet in the class, so I can't prove it at this point, but it's just useful to know this is true. Okay. So in general, it's hard to find the inverse of a matrix, but there is an algorithm, there's a method to do it, which I will explain. And the question is, should I just state what it is and then explain why it's true or not? Let me just show the algorithm so we get some practice using it. So this, page 3, and this is page 4. So let's recall what is reduced row echelon form of an m by n matrix. Doesn't have to be a square matrix or any rectangular matrix. So it has the following properties. First, every 0 row, that means a row with every coordinate 0, is below or under every non-zero row. Second, in each non-zero row, the first, as you go from left to right, the first non-zero coordinate is a 1. And in the column with that 1, every other coordinate is 0. And third, as you move down the matrix from one non-zero row to the next, the first non-zero coordinate, which is a 1, moves to the right. So for example, Just drawing an example of a matrix in reduced row echelon form. Okay, so this matrix, this is 7, is in reduced row echelon form. So first of all, this is how many rows and columns? 1, 2, 3, 4, 5. So this is a 5 by, and how many columns? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is a 5 by 10 matrix. There are 3 non-zero rows. And there are 2 zero rows. The 2 zero rows are at the bottom. The 3 non-zero rows are at the top. In each non-zero row, the first element that's non-zero is a 1. So in row 1, there's the first element. Everything else in that column is 0. In the second non-zero row, the first non-zero coordinate is a 1. Everything else in that column is a 0. And if you go from row 1 to row 2, the first non-zero element, that 1, is moved to the right. In the third row, the first non-zero element is a 1. In that column, above and below it are only zeros. When you go from row 2 to row 3, that first non-zero coordinate has moved to the right. The other coordinates can be anything at all. Right? Right. So this is a matrix in reduced row echelon form. So here's a way, it seems kind of like a miracle, but here's a way to find the inverse of a matrix. So suppose I take the matrix, I'll start with the case where we know the answer. Suppose I take matrix 3, 7, 5, 12. So this is 2 by 2. So I want to make a 2 by 4 matrix, same number of rows, but double the number of columns. I hand the left half, I write my matrix, and on the right half, I write the identity. So this is now a 2 by 4 matrix. And I want to put this matrix in reduced row echelon form. So the first thing I want to do is make this a 1. So I multiply the first row by a third. I get 1, 7/3, 1/3, 0. And the second row is still 5, 12, 0, 1. Okay. I want that to be a 1. I want a 0 here. So I have my first row, and I subtract 5 times the first row from the second row. So 5 minus 5 is 0. 12 minus 5, 5 times 7, 35 over 3. 12 is 36 over 3. So 36 minus 35, that's 1/3. 0 minus 5/3 is minus 5/3. 1 minus 5 times 0 is 1. So I got a 0 here by subtracting 5 times the first row from the second row. Then I want to get a 0 there. So I'm not changing the first row here, but I multiply the second row by 3. I get 0, 1, minus 5, 3. And then I want to get a 0 here in the column with this 1. This is 0, 1, minus 5, 3. And I take the first row minus 7/3 times the second row. So 1 minus 0 is 1. 7/3 minus 7/3 is 0. 1/3 minus 35, 1/3 minus 35 thirds is 1/3 plus 35 thirds is 36 thirds is 12. And 0 minus 7/3 times 3 is minus 7. So now I have a matrix where the first half is the identity. And what is the second half? Well, I calculated that as that was my first example. My first example, this is the matrix A, 3, 7, 5, 12, and the inverse was 12. This is minus 7, minus 5, 3. So somehow, it's kind of a miracle, you might say. I took my matrix whose inverse I want to find, wrote down a new matrix where I take the first matrix and then the identity. So I double the width, put this in reduced row echelon form. What I end up with here is the identity, and on the right half, somehow I got the inverse. So you might say that was pretty lucky. I would say that. It is pretty lucky. Let's do another example. And see if I can get the arithmetic right. Suppose I take A to be the matrix 2 minus 3, 0, 0 minus 1, 4, 6, 1, 0. So my method is double the matrix by adding the identity to it on the right and put that in that new thing in reduced row echelon form. So let me call this A sharp, say. So this is going to be 2 minus 3, 0, 0 minus 1, 4, 6, 1, 0. This line is not really there. That's just to make it clear what I'm doing. And then to the right, I put the 3 by 3 identity, 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. So this was a 3 by 3 matrix, and this is a 3 by 6 matrix. And I'm going to put this matrix in reduced row echelon form. So this is a lot of work, but sometimes you have to do a lot of work, right?
I have a question.
Yes, sir. Go ahead.
Why did you add the identity matrix to the A matrix?
Why? I'm telling you, this is the magic trick that works. Okay? I can explain why it works later, but I'm just showing you this is an algorithm that makes it work. It's no different when if someone tells you in high school, if you have the equation ax squared plus bx plus c equals 0, the solution is minus b plus or minus square root b squared minus 4ac over 2a. Now, you might not know where this comes from, but this is the solution, okay? So here I'm just telling you right now, I'll prove it later, but I just want everyone to see this is an algorithm, this is a method that always works to give you the inverse of a matrix. It does take a lot of calculation, so it may not be a good algorithm, but if you have a problem of finding the inverse of a 3 by 3 matrix, this method will definitely work. Okay? So the method is take your matrix and write down a new matrix, which is double the width, where you've added the identity matrix to the right of the given matrix, and put this in reduced row echelon form. So let's just do it and see what we get. All right? So I want the first non-zero coordinate to be a 1, so I multiply the first row by a half. I get a half minus 3 halves, 0, a half, 0, 0, and the rest doesn't change. Okay. Then, oops, sorry, I multiplied by a half, this becomes 1. That's the whole point. Okay. Then I want a 0 in the zeros in the column under the 1. Here there's already a 0. I just have to make this a 0. So I'm not changing the first row at this stage. I'm not changing the second row because I already have a 0 here. But I want a 0 here, so I subtract 6 times the first row. 6 minus 6 is 0. Minus 6 times minus 3/2 is 6 times 3/2 is 9. 9 plus 1 is 10. Minus 6 times 0 plus 0 is 0. Minus 6 times a half is minus 3 plus 0. 0 plus 0 is 0. 0 plus 1 is 1. So this is my matrix. So the first entry in the first row is a 1, and everything in that first column is 0. I want the first entry in the second row to be a 1. Well, that's easy. I just multiply the second row by minus 1. I get 0, 1, minus 4, 0, minus 1, 0. And I don't change the first or the third rows. 0, 10, 0, minus 3, 0, 1. 1 minus 3/2, 0. A half, 0, 0. Right. Then in this 1, in the column with this 1 in the second row, I want the numbers above and below it to be 0. So I have 0, 1, minus 4. 0 minus 1, 0 is the second row. If I multiply the second row by 3/2 and add to the first row, I get 0 plus 1 is 1. 3/2 minus 3/2 is 0. 3/2 times minus 4 is minus 6, plus 0 is minus 6. 0 plus a half is a half. 3/2 times minus 1 is minus 3/2, and 3/2 times 0 is 0. And let me just do the second step at the same time. I want a 0 here, so I take the third row minus 10 times the second row. 0 minus 0 is 0. 10 minus 10 is 0. 0. So I'm multiplying by minus 10 and adding, I get 40. Minus 3 plus 0 is minus 3. 0 plus 10 is 10. 1 plus 0 is 1. So if I've done this correctly, I have 0, 0, 40, minus 3, 10, 1, 1, 0, minus 6, a half minus 3/2, 0, 0, 1 minus 4, 0 minus 1, 0. Okay. What's the next thing to do? I want to get a 1 here. So the first row doesn't change yet. Second row doesn't change yet. But I divide the third row by 40. I get 0, 0, 1, minus 3 over 40, 10 over 40, which is a fourth, 1 over 40. And then the last two steps are to get zeros here and here. So the last row, 0, 0, 1, minus 3 over 40, 1/4, 1 over 40. If I multiply the third row by 6 and add to the first row, I'll get rid of this 6. 0 plus 1 is 1. 0 plus 0 is 0. 6 minus 6 is 0. Multiply this by 6. So minus 3 times 6 over 40, minus 3 times 6 is minus, let's see, 6 over 40. So that's 3 over 20. I get minus 9 over 20 plus a half, right? 6 times this. Let me do it simply. So 6 times this is minus 18 over 40 plus a half, which is 20 over 40. So minus 18 plus 20 is 2 over 40, which is 1 over 20. 6 times a fourth is 3/2, minus 3/2 is 0. 6 times 1/40 is 3/20. So when I eliminate this, oops, minus 6 to get a 0 here, that's what I did. I multiplied this row by 6 and added. I get 1, 0, 0, 1/20, 0, 3/20. And I want to get a 0 here, so I multiply the third row by 4 and add to the second row. 0 plus 0 is 0. 0 plus 1 is 1. 4 minus 4 is 0. Minus 3/40 times 4 is minus 3/20. 1/4 times 4 is 1. Minus 1 is 0. 1/40 times 4 is 1/10. 1/10. That was a 1. And now my matrix is in reduced row echelon form. And I claim that this is A inverse, right? So if it is, that's a miracle, but miracles are good. So let's just check. So my matrix A that I started with was 2 minus 3, 0. 0 minus 1, 4, 6, 1, 0. And this matrix, which I got on the right-hand side here, is 1/20, 0, 3/20, minus 3/20, 0, 1/10, minus 3/40, 1/4, 1/40. So let's just do this matrix multiplication and see what I get. I get 2 times 1/20, minus 3 times minus 3 is plus 9. So 2/20 is 1/10. Minus 3 times minus 3 is 9/10, plus 0. Second coordinate, I get 0, 0, 0. That's easy. The third coordinate, I get 6/20 minus 3/10, plus 0. Okay, that's the first row. Second row, I get 0, 3/10 minus 3 times minus 4 times 3/10. Then I get 0, 0. 4 times a fourth is 1. 0 minus 1/10 plus 4/40. And then for the last row, I get 6/20 minus 3/10, 0, 0, 0, 18/20 plus 1/10 plus 0. What is that? 1/10 plus 9/10 is 1. 0 is 0. 3/10 minus 3/10 is 0. 3/10, what was this? Second row, first column. 3/10 minus 3 times minus 4 times 3/40. That's 3/10 minus 3/10 is 0. 1. 1/10 minus 1/10 is 0. 0, 0. 9/10 plus 1/10 is 1. So this is the inverse. You know, if you want to check the multiplication in the opposite order, this times this, you also get the inverse. So somehow this process created, I mean, how you got it doesn't matter. If you have it and you check that it's the inverse, it's the inverse. The inverse of this matrix is 1/20, 0, 3/20, minus 3/10, 0, 1/10, minus 3/40, 1/4, 1/40. That's the inverse. All right. So again, if you can't add and subtract fractions, you're not going to do well with this, but this does work. We started with a 3x3 matrix. Wrote down the 3x6 matrix. Did step by step the process of putting this in reduced row echelon form. And we got the result. Right? So that's the algorithm, and you'll have numerous examples to practice it. But let me explain why it works, why it's true.
Can I see the other page, please?
This was just the check that this was the inverse. Right. So in order to understand why this works, we have to think a little bit harder about what it means to put a matrix in reduced row echelon form. So what are the elementary row operations? So there are three. The first is to interchange two rows. So suppose I take the identity matrix. I'm just using a 4x4 as an example. Suppose I interchange rows 2 and 3. So what I did here is I interchange rows 2 and 3. Here's row 2. In the new matrix, it becomes row 3. Here's row 3. In the new matrix, it becomes row 2. So here I interchange rows 2 and 3 in the identity matrix. And this new matrix is an example of what I'm going to call an elementary matrix. So an elementary matrix, what is this? This is a matrix obtained from the identity matrix by performing one elementary row operation. So this is an example of a 2x2, of a 4x4 elementary matrix, because I took the identity and I performed the elementary operation of interchanging two rows. What's the second elementary row operation? Multiply your row by a non-zero scalar. So for example, if I take the 4x4 identity matrix and I multiply the first row by 7, I get this matrix. And this is another elementary operation, because elementary matrix, because I got this matrix by performing the elementary row operation of multiplying a row by a non-zero scalar to the identity. So this is an example of another example of an elementary matrix. And the third elementary row operation is add a multiple of one row to another row, a different row. So if I take 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Suppose I multiply the first row by 4 and add it to the third row. So I don't change the first row. I don't change the second row. I don't change the fourth row. But if I multiply the first row by 4 and add it to the third row, I get 4, 0, 1, 0. So this is another elementary row operation. And you can write down every elementary row operation on an arbitrary matrix by multiplying that matrix on the left by an elementary matrix. So for example, suppose I have this matrix 2 minus 3, 0, 0 minus 1, 4, 6, 1, 0. If I take the elementary matrix I get by interchanging the first two rows of the identity, so if I take the identity and I make the first row the second row, and the second row I make the first row, and the third row I don't change. What happens when I multiply this elementary matrix by this matrix? I get 0 minus 1, 4, 2 minus 3, 0, 6, 1, 0. What happened when I went from here to here? I interchanged the first two rows. So the elementary matrix times this interchanges the first two rows. When I apply that elementary row operation to the identity, and I get the elementary matrix, and I multiply that elementary matrix to my matrix A that I started with, I carry out that elementary row operation. So in general, multiplying a matrix by an elementary matrix gives you the matrix, which is changed by exactly the elementary row operation that you did to the identity to start with. Like if I take 2 minus 3, 0, 0 minus 1, 4, 6, 1, 0, and I take the identity and I multiply, let's say, the first row by 4, and I multiply this times this. I multiply the first row of this matrix by 4, and I don't change anything else. So if you so this is what is the case. Let me just write it down explicitly. Perform any of the three elementary row operations. Perform an elementary row operation to the identity to get a matrix, I'll call it E. For any matrix A, these are all n by n matrices. The matrix you get by taking A and multiplying it on the left by this E gives you exactly the matrix A, gives you exactly the matrix that you get by performing that elementary row operation to A. So you can write elementary row operations in matrix form. So what that means is, let's see. Suppose I want to row reduce my matrix. So I want to put matrix A in reduced row echelon form. So how do I do that? I start with my matrix A and I perform some elementary row operation, which is the same as multiplying by a certain elementary matrix. Then I apply another elementary row operation, which is multiplying this by an elementary matrix. And then to this, I apply another elementary row operation, which is multiplying this by an elementary matrix. And step by step by step, as I put A in reduced row echelon form, I get a product of elementary matrices, such that product of matrices times A is the reduced row echelon form of A. If that reduced row echelon form is the identity, then EK, this product of elementary matrices times A is the identity, which means this is A inverse. Because this matrix times A is the identity. So if the reduced row, so this says the following: if A is an n by n matrix and the reduced row echelon form of A is the identity, then A is invertible and the inverse is this product of elementary matrices that you use to put A in reduced row echelon form. So if the reduced row echelon form of a matrix is the identity, then the matrix is invertible, and we have a way to find the inverse. Let's just sort of check this with the first example we did today. So in the first example, we had a matrix A which is 3, 7, 5, 11. So let's see how I can do this. So 3, 7,
It's
5.
12. It's 12, not 11.
Sorry? Oh,
It's
thank
3,
you.
7, 12.
3, 7, 5, 12. Okay.
Yeah.
That was the first matrix I started with. First thing I wanted to do was to make this 3 into a 1. So I applied the elementary row operation of multiplying the first row by a third. That's the same as taking the identity matrix, multiplying the first row by a third, and multiplying. So when I take this times this, what did I get? I got 1, 7/3, 5, 12. Right? Then I want to get a 0 here. So I want to multiply the first row by -5 and add to the second row. So if I take the elementary matrix, so let me do that to the identity. If I have the identity, if I take the first row times -5 and add to the second row, that's what I get. So I'm multiplying 1, 0, -5, 1. Right? So when I do this, what is it that I get? I get 1, 7/3, 0, -35 over 3 plus 12 is 1/3. Right? So now this matrix times these two elementary row operation matrices, two elementary matrices gives me this. Then I want to make this a 1. So I want to multiply this second row by 3. So if I take the elementary matrix and I multiply the second row by 3, I get that. And what do I get? I get 1, 7/3, 0, 1. And then the last step is I want to get a 0 here. So I want to not do anything to the second row, but I get a new first row by adding 7/3 times the second row to the first row. So if I take the identity and I add 7/3 times the second row to the first row, I get that. So this should be a multiplying by 1, 7/3, 0, 1. And now, what do I get? I get, oops, I did something wrong. I want to multiply the second row by -7/3 and add to the first row. So this is 1. When I multiply, I get 1, 7/3 -7/3, 0, 1. I get the identity. So here I have a product of 4 elementary matrices. And this product times the original matrix is the identity. So this product is A inverse, right? So if you multiply all this out, you should get A inverse. I should add, of course, that every elementary matrix is invertible. Because if you get a matrix, if you interchange 2 rows, if you interchange the same 2 rows again, you're back where you started. If you multiply a row by a non-zero number C, then if you multiply that same row by the non-zero number 1 over C, C times 1 over C is 1, you're back where you started. If you add C times a row to another row, then if you add minus C times that row to your new row, you cancel the first operation, you're back where you started. So every elementary matrix is invertible. So every product of elementary matrices is invertible. And this is how we can get the inverse of an arbitrary matrix. Well, this is the first observation. So let's see why that trick I explained before of doubling the matrix by adding the identity gives the inverse of a matrix. Suppose A is an n by n matrix. And I write the matrix, let me call it A sharp, which is like A on the left and the n by n identity on the right. Right? Now I want to put this matrix in reduced row echelon form. I do that by performing a sequence of elementary operations. So if I take, for example, E1 times A, what that's going to give me is E1A, E1 times the identity. If I multiply that by a matrix, elementary matrix E2, this is going to give me E2, E1A, E2, E1. And I keep on going. I do this K times. And what do I get? Here, this matrix is in reduced row echelon form. And if that's the identity, then over here I have EK up to E1. But this was exactly A inverse. These are the sequence of elementary matrices that give you the matrix A. Again, I'm always sorry that my writing is not fantastic, but in any case, it's all in the book. It's all in the notes, legible and very clear. So what I've just proven, I've defined an elementary matrix. I've explained why an elementary matrix is invertible, and so a product of an elementary matrices is invertible. If you put a matrix in reduced row echelon form, then you can get that form if your matrix is A, the multiplying on the left by a sequence of elementary matrices gives you the reduced row echelon form of the matrix. And if that reduced row echelon form is the identity, then the product of elementary matrices is the inverse. And in that case, applying those elementary row operations to this matrix A sharp, where I doubled it by writing A as the left half and the identity on the right half, the new result will be the identity on the left half and the inverse of A on the right half. So what's left is to show that if a matrix is invertible, then its reduced row echelon form is the identity. Because if the reduced row echelon form is the identity, we've seen that it's invertible and the identity and the inverse is a product of elementary matrices. So there's a proof in the notes, and I want to see what's a nice way to explain this. So in the notes, this is lemma 2.8. It says that if A is an n by n matrix, and R is the matrix in reduced row echelon form, that's row equivalent to A, and A is invertible if and only if R is the identity. So if that reduced row echelon form is the identity, the matrix is certainly invertible. So conversely, if A is invertible, let's see. Let me write this out. So this is in the notes, lemma 2.8. So lemma 2.8 says that A be an n by n matrix. Let R be a reduced row echelon matrix that we got from A by elementary row operations. So that is row equivalent to A. So that means R is obtained from A by multiplying by, let's say, L elementary matrices. Let's call this matrix S. This is S times A. So if R is the identity, then S is A inverse. If the reduced row echelon form of the matrix is the identity, then the matrix is invertible, and the inverse is this product of elementary matrices. Okay, but what about the opposite case? So conversely, let A be invertible, and let the reduced row echelon form of the matrix, this is S times A. So A is invertible. The product of elementary matrices is invertible. So the product of two matrices is invertible. So this is invertible. So R is the reduced row echelon form of the matrix. So what does R look like? R is a series of rows. Now, if R is not the identity, then, see, if R is the identity, every row has to start with a 1. If R is not the identity, then R has at least one non-zero row. So R is some matrix with at least the bottom row equal to zeros. Other stuff is whatever it might be. And this is S times A. So R has its last row, the nth row is the 0 row. But for any matrix M, any n by n matrix, if I take R times M, the last row is always going to be 0. And if M were invertible, if R were invertible, I could take M to be R inverse, and the last row would have to be have a 1 here, which is impossible. So if A is invertible, then its reduced row echelon form must be the identity. And that is a somewhat subtle proof of this fact. What's written in the text, lemma 2.8, the proof is exactly correct, but it does take a certain amount, maybe a lot of time and thinking to understand the argument. This also says that the inverse of A is a product of elementary matrices, which means that A itself is a product of elementary matrices. So these elementary matrices are really like, they're almost like the atoms in a molecule. You put together these products of elementary matrices and you get every invertible matrix. Not in a unique way, but in some way. So this is the last theorem in this section, which says that an n by n matrix is invertible if and only if it's a product of elementary matrices. So that is the story. Let me do, let's see. There's one more result in this section. It's lemma 2.11, which says the following are equivalent. A is invertible, A has a left inverse, and A has right inverse. And just for completeness, let's say, let me try and show why this is the case. And this is also related to the problem we started our course with, which is solving systems of linear equations. So let me do all of this. And so this is, in my notes, is lemma 2.9. So A is an n by n matrix, and the following statements are equivalent. So remember, we can write a system of equations in matrix form, A x equal B, right? This is n linear equations in n variables, right? If you were to write this out, it would be A11 x1 up to A1 n xn equals B1 down to the last equation, AN1 x1 plus ANN xn equals B sub n. So taking this system of equations and writing it in matrix form, you get AX equal B, where A is the matrix of coefficients of the equations, and B is this column vector. So the following are equivalent statements. For every B in Rn, AX equal B has a solution and only one solution. Has a unique solution. Second, the homogeneous equation is a special case. AX equals 0 has a unique solution. The third equivalent statement says that A, that matrix, is invertible. And if A is invertible, then every one of these equations has a unique solution. So proof. Why does statement 1 imply statement 2? Statement 1 says that for every B, AX equal B has a unique solution. So in particular, if I let B equal 0, and AX equals 0 has a unique solution. So this is kind of trivial. Let me skip 2 implies 3 for the moment. What about 3 implies 1? So A is invertible. So if you want to solve AX equal B, multiplied by A inverse AX equal A inverse B, but A inverse A is the identity. So if you let X be equal to A inverse B, A times A inverse B is the unique solution. So if A is invertible, if you would take X to be the vector A inverse B, that's the one and only one solution of that equation. So 1 implies 2, and 3 implies 1. So we want to show that 2 implies 3. We want to show that if the homogeneous system of equations has a unique solution, then A is invertible. So we know A is invertible if and only if the reduced row echelon form of the matrix is the identity. Right? So there's a matrix S. Well, so SA equals the identity for some matrix S. S is S inverse. Right? So I want to show that if the homogeneous system has only the 0 solution, then the matrix is invertible. So suppose AX equals 0 has only the 0 solution. We have the reduced row echelon form of the matrix R is equal to SA for some invertible S. And if R is not the identity, then in the matrix R, the last row is all 0. So if I take any vector how do I want to say this? I'm interested in AX equals 0, where A is an n by n matrix. And we're going to suppose the only solution is the vector X equal to the 0 vector. Right? Must show, this is what I want to show, that A is invertible. So there exists an invertible matrix S with S times A equal to R, which is the reduced row echelon form of A. So A is invertible if and only if R is the identity. Suppose R is not the identity. So then the matrix R, it's an n by n matrix, but the last row is all 0. So these are the first n minus n rows, and then I have this last row. Then we call R prime be the n minus 1 times n matrix, which is the first n minus 1 rows of R. And suppose I want to solve the equation R prime x prime equals 0. So this corresponds to n minus 1 equations in n variables. But we showed that if you have more variables than equations in a system of in a homogeneous system of equations, there's a non-zero solution. So there exists x prime not equal to 0 with R prime of x prime equals 0. X prime has dimension n minus 1. Suppose I let x be x prime, adding a 0. So this is not the 0 vector. Of course, x prime is not 0. Then Rx is actually going to be all zeros, because R prime times x prime is 0, and the 0 row times anything is 0. So if the reduced row echelon form of R is not the identity, then the homogeneous systems of equations has a non-zero solution. So for those of you who are thinking about majoring in math and have to learn something about abstract mathematical reasoning and proofs, this is really something hard but important to try to understand. But in some sense, it is maybe too hard if you're not going to be a math major. And I would never ask you to reproduce a proof like this on the exam. So maybe this is just a kind of a moral lesson to show that you shouldn't make statements in mathematics that don't have proofs. And here is a proof. So these are somewhat deep facts about systems of linear equations and matrices. A matrix is invertible if and only if its reduced row echelon form is the identity. A matrix is invertible if and only if it's a product of elementary matrices. A matrix is invertible if and only if the corresponding system of linear equations always has a unique solution for every right-hand side vector B. And a matrix is invertible if and only if it has a left inverse or a right inverse. So these are all important statements about matrices, which I certainly encourage you to think about. But and the more you think about it, the deeper you understand what's going on, I guess. Okay. That's it for today. Let me again remind you, 2 weeks from today on campus is the midterm. And I'll send out an email announcement to everyone today also to make sure everybody knows. Okay, well, any questions before we end for the morning? or early afternoon. Okay. All right, be well all. Bye-bye.
Thank you.